Welcome back, BMRI students. I'm absolutely thrilled you're here for Episode 9, Sound is Medicine. In today's explainer, we are completely stepping away from X-rays. We're leaving ionizing radiation behind. Instead, we're looking at something truly remarkable and honestly kind of mind-blowing: sound. Specifically, medical ultrasound. It is literally one of the most widely used, versatile, and dynamic diagnostic tools in all of clinical medicine. And today, we're going to demystify exactly how it works.
Okay, let's dive into this. How do we take an invisible physical force, right, a simple sound wave, and translate it into a real-time moving picture of a beating human heart or a developing fetus, all without a single drop of radiation? Honestly, it sounds a bit like magic. But as you'll see today, it's just pure, elegant physics.
So, here is the concept to clinical journey we'll be taking today. We'll start with the physics of medical sound, look at creating waves with the transducer, trace sound's journey through tissue, cover the visual display modes, and finally wrap up by catching movement with Doppler physics.
Section 1. The physics of medical sound, beyond human hearing.
To really understand ultrasound, we first have to recognize that sound is a mechanical, longitudinal wave. It's made of compressions and rarefactions. And crucially, it absolutely requires a medium to travel through. It needs matter. Now, ultrasound specifically refers to waves operating way above human hearing, anything over 20,000 hertz. But for diagnostic imaging, we're using frequencies from 2 to 15 megahertz. That's literally millions of cycles per second. And unlike X-rays, which can happily travel through the vacuum of space, these mechanical sound waves cannot propagate through a vacuum. No matter, no sound.
And this brilliantly illustrates why different materials matter so much. Sound travels at totally different speeds depending on what it's moving through. Take soft tissue, for instance, sitting at exactly 1540 meters per second. That number is absolutely critical to remember. Your ultrasound scanner just assumes that every single wave it sends out is traveling at exactly 1540 meters per second. That calibration is exactly what allows it to measure depth and distance inside the body. But think about air, which is way slower, or bone, which is massively faster. When sound hits gas or bone, it completely throws off the machine's assumptions, introducing errors or even blocking the image entirely.
Section 2. Creating waves. The transducer.
So how are we actually creating millions of sound waves every single second? Well, the answer is the transducer. This is that wand touching the patient's skin. It's the exact place where electrical energy meets mechanical energy. Inside the transducer are these special crystals, traditionally made from a material called PZT, or lead zirconate titanate. These crystals possess a remarkable property called the piezoelectric effect, and it's basically a two-way street. In step 1, the machine hits the crystal with an electrical voltage. The crystal physically deforms and pulses out a mechanical sound wave. It literally shouts. Then, in step 2, a returning sound wave, an echo, comes back and hits that same crystal, physically compressing it. That compression generates an electrical voltage the machine can then read. It's pretty amazing when you think about it. The exact same element is acting as both the speaker and the microphone.
Section 3. Sound's journey through tissue, echoes and obstacles.
Now, once that wave leaves the transducer and meets the tissue, we run into something called acoustic impedance mismatch. See, when sound strikes a boundary between two different tissues, some of it bounces back as an echo. The greater the difference in density between those tissues, the stronger the echo. But here's the catch. The mismatch between human skin and the air in the room is enormous. If you put a dry transducer on dry skin, you get essentially 100% reflection right at the surface. You'd see absolutely nothing inside the body. So the crucial point is that cold gel your doctor squirts on you. It isn't just a lubricant. It actively eliminates that air wall, providing the acoustic coupling needed so the sound can actually enter the body.
As that sound travels deeper into tissue, it slowly gets absorbed and converted into heat. And this absorption creates a massive clinical trade-off. High-frequency waves, those 7 to 15 megahertz ones, give us beautifully crisp, high-resolution images, but they get absorbed very, very quickly. So we can really only use them for shallow, superficial structures, like the thyroid, or maybe blood vessels right near the skin. On the flip side, low-frequency waves in the 2 to 5 megahertz range give us lower resolution, but they can penetrate much deeper. That makes them perfect for looking deep into the abdomen or the pelvis. It's always a balancing act.
Moving on to Section 4. Display modes, visualizing echoes.
So how does the machine actually display these returning signals to us? Historically, the whole thing started with A mode, which stands for amplitude mode. A single pulse goes out, and returning echoes are just displayed as vertical spikes on a time-axis graph. The taller the spike, the stronger the echo, And the further to the right the spike is on the screen, the deeper the tissue. It's absolutely brilliant in its simplicity. And believe it or not, it's actually still used today in highly specialized fields like ophthalmic biometry, just to measure very precise distances inside the eye.
But let's move to B mode, or brightness mode, and see how this builds into the standard 2D images we're used to seeing. B mode takes those A mode spikes and converts them into a line of grayscale dots. A really tall spike becomes a bright white dot, a smaller spike becomes a gray dot, and if there's no echo at all, it's just black. By sweeping thousands of these lines side by side continuously, the machine builds up a beautiful, real-time, two-dimensional cross-section of the anatomy. This is your classic ultrasound image.
And then we have M mode, motion mode. Imagine taking just one single vertical line of that 2D image and continuously scrolling it horizontally across a screen over time. What you end up with is a highly dynamic record of moving echoes. If you run M mode right through a beating heart, you can visually track the exact precise opening and closing of a heart valve. Or you can beautifully document the exact rhythm of a fetal heartbeat. It is an incredibly powerful way to capture motion in real time.
Section 5. Catching movement. Doppler physics.
Now this is where things get really dynamic. We're shifting from looking at stationary organs to tracking the flow of microscopic red blood cells. To pull this off, we rely on the Doppler effect, famously described by Christian Doppler way back in 1842. The core principle here is that when sound bounces off a moving target, its frequency actually changes. If red blood cells are moving toward the transducer, the reflected sound wave is compressed, and the frequency goes up. If they're moving away, the frequency drops. That difference between the transmitted and reflected frequencies, that is the Doppler shift, represented mathematically by the symbol delta F.
Now, what's really fascinating about this is how the math directly dictates our real-world clinical practice. Remember the cosine theta in that equation? That represents the physical angle between our sound beam and the blood vessel. If the beam is perfectly parallel to the blood flow, essentially a 0-degree angle, the cosine is 1, which gives you perfect 100% sensitivity. But if you hold the transducer straight down at a 90-degree perpendicular angle to the vessel, the cosine becomes 0, and at 90 degrees, the entire Doppler equation multiplies by 0. The machine goes completely blind to the blood flow. That's exactly why ultrasound technologists are always carefully angling their probes, aiming for that sweet spot between 30 and 60 degrees.
Modern scanners actually give us a whole toolkit to visualize this flow. Spectral pulsed wave Doppler lets us sample flow at a very specific targeted depth. Continuous wave Doppler, on the other hand, casts a wide net with no depth limit, which lets us measure incredibly high-velocity jets, like what you'd see in a severely restricted heart valve. Then there's color Doppler, which paints a vibrant spatial map right over our anatomy, typically red for flow moving toward the probe and blue for flow moving away. It's amazing for instantly spotting things like a deep vein thrombosis. And lastly, power Doppler. This one throws out directional data entirely in favor of ultra-high sensitivity, letting us detect the tiniest trickle of flow inside small vessels, or helping us assess the vascularity of a tumor.
Section 6. Key takeaways.
All right, let's wrap up with the core of what we've learned today in this concept to clinical journey. Diagnostic ultrasound uses 2 to 15 megahertz mechanical waves, which we assume travel at exactly 1540 meters per second in soft tissue. Those waves are generated and received by the two-way street of PZT crystals. Remember, we absolutely must use gel to eliminate the acoustic impedance of air. We visualize these echoes using A, B, and M modes, moving from simple spikes to real-time 2D anatomy and precise motion tracking. And finally, we leverage the Doppler effect to track the direction and speed of blood flow based on angle-dependent frequency shifts.
Which leaves us with this final thought. Right now, we are using harmless, silent vibrations to map the intricate, hidden plumbing and beating rhythms of the human body in real time. As computational power continues to grow and our crystals get even more sensitive, if manipulating mechanical waves allows us to see blood rushing through the heart today, what other invisible rhythms of the body might sound eventually reveal? Thank you so much for joining me on this explainer. Keep learning, keep questioning, and I'll catch you next time.